right, so you should see my slide come back up now. It's hard to tell what motivates people to join, but we went, I think you had like 120 in one class, and then you can have like 20 in the next. So welcome to everybody who's joining us in Zoom or in the YouTube live stream. It's just about 12:57 right now, so we'll get started with Earth's energy balance in about 3 minutes.
Do you not have an office space at home?
I do, but I plug into the Ethernet to make sure the quality is higher. So unfortunately it's down here in the living room.
We've got the server in the basement, so there's Ethernet everywhere we want it to be.
Yep. So welcome everybody joining us in our Zoom meeting or on our YouTube live stream. We just have about a minute to go. I'm gonna wait in case any last folks are gonna be joining us. We'll get started with Earth's energy balance just right at 1 o'clock at the top of the hour. All right, I'm going to stop sharing my screen and welcome everybody who's joining us on Zoom or in our YouTube live stream. We're excited to have you here this afternoon with us for our 1 p.m. class on the Earth's energy balance. My name is Drew Bush and I'm the Director of Programs at the Fairbanks Museum. In a moment, I will turn things over to a voice that might be familiar to all of you, Chris Kurdek, one of our Eye on the Sky meteorologist team members. But first, I just wanted to quickly let you know if you're in Zoom how to participate. You can move your mouse to the bottom of the screen and you'll see that there's a Q&A button and you can actually write your questions right in that Q&A. And we will see them and I will either get Chris to answer them live or we'll type in an answer and reply to you. You can also pose your questions on there anonymously. And as some people have probably already noticed, there's also a chat screen. And on that chat, you can type to one or all of us. So you can specify if you want to talk to Chris or myself or to other people who you might see in the meeting. And then finally, you can also, if you're on our YouTube live stream, take part in today's class with the chat that you'll see right on the upper right of your YouTube live screen. And just a word of note for you, we are video recording this class and we'll be posting it in our archives at fairbanksmuseum.org. So please be aware of that when you do ask your questions. And of course, I just lastly want to welcome everybody who might be joining us later on Kingdom Access Television or another cable affiliate in the state of Vermont. But without further ado, I will turn things over to Chris Kurdek now for our 1 p.m. class. Thank you.
Hi, my name is Chris Kurdek, and I'm a meteorologist and science educator at the Fairbanks Museum in St. Johnsbury, Vermont. If you do see my setup here in my spare bedroom / office / recording studio, I do have some extra padding as I do the radio weather forecast from this station as well. So I'm not trying to block anybody out behind these blankets, but I do have to do a little bit of padding. So today we are going to talk about the Earth's energy budget, also known as the Earth's energy balance. I'm going to share my screen here. And we're going to start here. As you guys can see, it says the Earth's energy budget right there, also known as a balance. A balance, if you have a balanced budget, that means you're doing something right. If you have an unbalanced budget, you're probably doing something wrong. So without further ado here, Earth's energy. So energy has the ability to change its surroundings. Examples: fuel for a car, ball falling from a window, or electricity when you turn on the light. So the way the light switch works is it's a switch, so the gate kind of opens and closes and lets the electricity go through and turn on the lights. A budget, if we're not too familiar with a budget is, we also, if you're a kid, your parents are always bugging you to budget your time to do your chores on the weekend so you can go outside. Or money is also another budget we're very familiar with. If you're spending more money than you have, well, that's probably not a good budget. Or for instance, if I wanted to go out and buy a video game with my money, I would probably have to budget for a week or so ahead of time to make sure the funds were there. But a budget is the amount of something that is incoming or outgoing in a certain situation. So again, time and money is what we often use, but we also have an energy balance when it comes to the Earth as well. Equilibrium. So equilibrium is a state of balance. So if your emotions can be in an equilibrium, if they're not, you might be maybe the most not happy or kind of sad. Chemical reactions are also a very common equilibrium. You know, if we put some gasoline in our car, it'll probably be pretty in a very equal state. If we take a match of that gas, well, I think everybody knows what happens afterwards. The chemical reaction happens and not too much of an equilibrium. And then forces also is something we talk about in science, that the forces is what we talk about in science, and that's also can be equal or opposite forces. Equilibrium means, though, the total amount of change over time, but the budget for phase stays fairly the same. So a question here, if anybody is able to answer it. What are the different types of energy? So there's different types of energy we receive. I don't know if we have any participants in here right now, or if anybody wants to chime in on YouTube as well, but I'll give us a moment or two to see if we do have anybody.
So a couple of people are saying heat and light.
Absolutely.
I think those are the two we have on YouTube right now.
Okay, I'll give a second if somebody else. Heat and light, they actually kind of go in the same department of energy. Radiation is that type of energy, which is actually the type of energy we're going to be talking about today.
A few people are talking about electricity and fossil fuels.
Fossil fuels, absolutely. That comes through combustion. So, but again, mostly radiation is what we've stepped on. If anybody else wants to chime in about other types of energy we might know about, maybe pertaining to machines, or again, we talked about it, what happens when, you know, I take a match to a flame to gasoline. That's a type of energy that is made there as well.
One person is saying mechanical.
Absolutely. Mechanical energy. Absolutely. Just like as I hinted with machines. Absolutely.
Not seeing that many more responses.
All right. So I'm going to keep on going here. And I have a little diagram here. Types of energy. So we do have a mechanical energy, or a car moving, a frog leaping. Thermal energy, heating up soup or ice cream melting. Nuclear energy, also known as a type of radiation, and nuclear fission inside the Earth's core, as well as fusion of the sun and the stars, which is actually what we're going to be talking about today. but I'll be using the word radiation more than so than nuclear. Chemical, again, so chemical energy, I really like this for chemical energy is people eating food, right? So we eat the food where if it's a vegetable, mostly likely the energy comes from the sun because of photosynthesis. We eat the food and then that gives us energy. One point when I was a middle school teacher, I always would like to tell my students is that we deal with energy a lot more than you'd think. If you looked on the side of maybe, I don't know, a bag of Cheerios or any type of food, we actually measure the amount of food we're receiving in the form of energy in calories. And calories is just a measurement of energy. But it's kind of weird that we don't really look at it that when we think about food, we think about how much we should take in or how much we should budget when it comes to calories a day. But calories is at the end of the day, it's just a form of measurement of energy. Back to chemical energy, again, striking a match. We're also putting that to gasoline. There's a chemical reaction. If there's any sort of heat or energy transfer, therefore there's a chemical reaction. We have electrical energy. We've talked about power lines and light switches, as well as some lightning. Electromagnetic is all, and we also have different types of waves of energy, as well as sound is another form of energy, which is not listed here. But I do have another question here, and I might have hinted already. When it comes to the Earth's energy, where does the Earth's energy come from, and what type of form is it in? So I'll give everybody a moment to answer on YouTube if they do have a moment.
It looks like people are saying the sun and light as the form.
Absolutely. So the form of energy or the light energy, but the sun does give us light. It's actually visible light. So there's different wavelengths of light that we can see and we cannot see. Sorry about that. So, but it does come in the form of light or radiation, because what happens is there's fusion that happens between the molecules in the sun, and there's all these kind of mini explosions, and it sets off the radiation all the way to the Earth. So again, it will be in the sun. The sun is where we get all of our energy from here on the Earth, and it comes in the form of radiation. So incoming light here is called short wave energy, and we're going to get in a little bit more in detail about what happens when this energy hits the Earth, because it all doesn't kind of go along the same path. So we have the Earth-Sun model here, and what is the Earth-Sun model? And what is the model of the Earth? And where is the equator? Where is the North Pole? And where are you? So as we do know that the Earth is tilted on a 23.5 degree axis right here, and we spin around it, and we know that the equator is that imaginary center line that goes through the Earth. And if you're tilted towards the sun, you're going to receive a little bit more light or energy from that. So light and energy kind of all the same. If you're tilted away from it, you're more likely to you will receive less energy. If you are listening in northern Vermont, as where the museum is from, I often ask my students that we have all these, and especially if you are in Vermont, we do have these kind of borders that surround us from the north, south, and east and west. Does anybody want to maybe cue in what might be the border between New Hampshire and Vermont on YouTube?
And you can also feel free to cue it in the Zoom chat. So I think people are saying east as the border.
East, okay, so there's actually it's actually a land, not a land border, but it's actually a river that goes between Vermont and New Hampshire. It's the Connecticut River, and it's a pretty defined border, as that is our border between New Hampshire and Vermont, the whole length north to south. And then if we go over towards New York, we have another border, which is part of the topography, which is Lake Champlain. But has anybody ever realized why we have a straight line for a border with Canada? Maybe someone can chime in what our border with Canada actually signifies, kind of pertaining to this model we have going on right here.
think the only thing I'm seeing is a question mark. I'm not sure people know the answer.
Okay, so Vermont, we do have some pretty a pretty drastic change in seasons here, and so we do have the equator, which is 0 degrees right here, and then we have the North Pole, which is 90 degrees north, and we are actually halfway between the equator and the North Pole. So we have the latitude of 45 degrees, or the 45th parallel is our border with Canada, or Vermont's border with Canada. And that is exact midpoint between the equator and the North Pole. And that's all. So therefore, we have a large change in our sun throughout the year, or the amount of sunlight we get throughout the year, as well as the amount of radiation we receive from the sun throughout the year. In the wintertime, we receive less radiation from the sun. Therefore, we're able to lose more energy than we gain. And we're able to kind of accrue a pretty deep snowpack on the ground. But I'm going to go a little bit more in depth about that now. So back to our budget, right? We all have to have an input or an output. So the sun emits radiation, and then the Earth intercepts that. And some of that hits the ground and we absorb it, but some of it also kind of bounces back out. So another part of our budget here is sunlight is the form of energy we receive. Sunlight comes in a range of short wavelengths called visible light, which is what we're able to see, and it comes to the Earth as short wavelengths. And this is just kind of just a model of what wavelengths are, just like you would see waves on the ocean when you're at the beach. They have different they're a little bit wider between the crests over here, as you can see, and they're a little bit shorter here. And this is the short wavelengths we receive from the sun, opposed to the longer wavelengths. So once the sunlight reaches the Earth's surface, what happens?
Well, so we actually have a question from somebody. Isn't a lot of the sunlight, isn't it blocked in space as it travels to the Earth? Or are there other things that intercept it, I guess is what they're asking.
That's a great question. And I'm not going to give an answer to that just yet, because I'm pretty sure we're going to see some of these answers in a couple moments. So I did like that kind of comment or question there. So definitely on the right path on where this lesson is going. If anybody else wants to chime in about once the sunlight reaches the Earth, what happens?
One person says it goes into plants and photosynthesis.
Absolutely. Great job there. I would totally agree with that. So I would say if it goes into plants, it is absorbed by the plants. Give us a couple more seconds here.
Another person said it might bounce off of things like the surface of the ocean or snow or ice. Another person saying the Earth gets heated up by it.
Absolutely. Great job there. So I think we're all on the right path with this. And I think it all comes down to dependent on the type of surface. So some surfaces absorb sunlight or radiation a lot easier than others, where others reflect it. And we're going to talk about that right now. So again, just use those words. I'm a little ahead of myself though, but if something is reflected, it bounces off, or if something is absorbed, it's taken or held in. As you hear, you usually don't talk about the reflection of energy waves so much, but when we do talk about reflection, we're talking about maybe a reflection in a mirror, as you can see here, or even I can see my reflection in the web camera right now. But also, again, there's also energy that is absorbed or taken or held in. So I think everybody who answered was pretty correct as what happens to the solar radiation when it comes into our Earth. About 50%, or 48 to be exact, about 50% though is absorbed at the surface of the Earth. But we also have this blanket that surrounds our Earth known as the atmosphere that we are very lucky to have, because it wouldn't be a very hospitable world to live on if we did not have the blanket of the atmosphere. And 23% of it is actually absorbed in the atmosphere itself. And then 29% of it travels a really long distance. It's kind of like going, I don't know, on a really long trip and having to turn around as soon as you get there. So as it makes it all the way here and it bounces back off the atmosphere and the Earth's surface as soon as it gets here. So that radiation never really finds its way to Earth. So we are going to watch a quick video about the Earth's albedo. And this kind of, the albedo, I know it can be maybe a bigger word that maybe some of us aren't the most familiar with, but all albedo is, it shows you how much a surface is able to reflect or absorb radiation from the sun. And just give me 1 second, because I got to set up some speakers here too. Hold on. The Earth receives energy from the sun.
Some of which is reflected back to space. Albedo is the fraction of this energy that is reflected. Albedo is critical for the Earth's energy balance and climate. For temperatures to stay in the same range from year to year, incoming solar energy must, on average,
Is that loud enough,
equal
Drew?
outgoing energy. Bright white clouds reflect the most sunlight and therefore have the biggest impact on Earth's albedo. These weekly maps are reflected solar radiation for the past 10 years. Lighter colors show more reflection and darker colors show less.
So as we can see here, though, as we go through the months, maybe if we can go back to maybe March, we are experiencing our winter up here, and snow is really good at reflecting, or the northern hemisphere is really good at reflecting the sunlight's radiation, or the radiation from the sun. Therefore, we reflect more up here. We're down here. This is kind of the forest, or the Amazon forest down that way. So therefore, it absorbs more, as well as the fact that it is their summer in the southern hemisphere. But we're going to talk about that a little bit more.
And darker colors show less. Notice more reflected solar energy where there are persistent clouds, wind-blown dust from the Sahara Desert, smoke and pollution, and over snow and ice. One way humans impact the global energy balance is by modifying the Earth's albedo through industry and transportation, such as ship tracks and jet contrails. Agricultural burning and land use change also modify albedo. These land albedo maps show how reflective Earth's surfaces are from month to month. Bright areas with snow and ice have high albedos that can be close to 1, meaning almost all of the sun's energy is reflected back to space at these locations.
And again, as you can see here, a very cold spot is Greenland. And as you can see here, because it's mostly covered with snow most of the time, therefore it reflects a large magnitude of the radiation back out off the surface. And we're going to keep talking about albedo a little bit more, so I'm going to keep going here.
Gray areas are missing data, either caused by persistent cloud cover or lack of sunlight. Notice that missing data peaks at the North Pole in December and at the South Pole in June. Deserts are brighter and more reflective in places with thick vegetation, such as rainforests. The albedo of the ocean is not shown here, but is generally low, less than 0.1 if clouds are not present. The brightness of clouds, airborne particles, land surfaces, and the ocean all contribute to the Earth's energy balance and climate. There's still a lot we don't know about how much sunlight is reflected back to space and how humans impact albedo.
All right, thank you for listening to that there. We're gonna head on back to the PowerPoint here. Uh-oh. Give me 1 second, guys. Uh-oh. Oh, backtracked here. There we go. All right, so we're going to keep going here. So Earth's... Oh. We got to sneak up here, guys. Sorry about this. All right, so albedo equals reflection. Albedo and reflection kind of go hand in hand. They're kind of the same type of premise there. So we use a scale of 0 to 1. So white is, I think many of us are familiar with this. If you wear kind of a lighter colors when it's warmer during the summertime, you're more likely to be hotter. So whiter has a higher reflectivity, or a reflectivity of 1 when it comes to their albedo, where black would be 0, has a very low reflectivity. So it's very good at absorbing the radiation from the sun. I can use a couple examples here. Again, if we use the black t-shirt to a white shirt on a summer day, you're definitely going to be absorbing, that black will be absorbing more of this radiation from the sun. You'll definitely be a lot hotter in that black shirt than that white shirt. What do you guys think here? Maybe we could start with grass. Do you guys think that has a high or a low albedo? Or you could just say if it's very good at reflecting or absorbing the sun. So maybe we could just go with a reflecting or absorbing the sun for grass here, if anybody wants to chime in.
It looks like most people are saying absorb.
So yeah, it does a fairly good job. Maybe it doesn't absorb as well as maybe some other these surfaces that we're going to get to on the list, but it does. And as we know, grass goes through the process of photosynthesis, so it needs that energy from the sun to produce, to be able to grow. Therefore, it does a decent job of absorbing. There are other surfaces that maybe do a little bit better, but I would say it's better absorbing than reflecting. What about ice, which we kind of just hinted to in our last video? And think about the color of ice as well, which we've kind of discussed right here. Good job. Thank you, whoever's in our chat here. So he said, or she said, they said that ice is good at reflecting. And as we did see in that last video, when we did see the winter time on the poles, it is white. So therefore it is very good at reflecting. And actually, snow and ice reflects about 90%, if not more, sunlight from the radiation back from the sun out into the atmosphere and outer space. And if you ever realize, it's kind of, we call this a runaway process. But once you get into the winter time, you know, if you get a good snowpack on the ground, you're more likely going to have colder temperatures because of that, due to the fact that you are kind of radiating out all of that energy back out to the atmosphere as well as out to outer space. Whereas if you had maybe more of a grassy surface that wasn't as good as reflecting the energy, you'd most likely get some warmer surface temperatures throughout the day as well. And I think we can kind of put all these three together: rocks, asphalt, and concrete. Or maybe just, what do we think they are good at reflecting or absorbing the sunlight from the radiation from the sun?
So I think they're saying reflecting.
So
by and large.
Okay. So these are actually good at, depends on the color of the rock I have over here. I agree with that if it's maybe a quartz or something that's more of a whiter rock. But overall, these substances or these surfaces are really good at absorbing the sunlight. So we can use the example for rock. Say it's a very hot summer day and you're hanging out by a lake or something like that, and the sun is setting and it's cooling off. And it happens pretty quick here sometimes in Vermont in the summertime. But that rock is actually going to be warmer than the surface air. If it's a big enough rock and it was baking in the sun throughout the day, it's actually going to be warmer than the surface temperature or the air temperature around it. Therefore, that signifies it's really good at absorbing the radiation from the sun, especially if it's a black rock such as asphalt, which is often black. But also you can kind of use, if you've ever seen, or if any has a lizard, usually they'll have like a heating rock. If somebody has a lizard, or if they're in the wild, lizards like to kind of hang out on the rocks because they like absorbing the heat that is absorbing out of the rock, as well as concrete is a fairly good absorber of radiation from the sun. Again, sometimes concrete's more white, so the color can affect it. But I want us to kind of keep in mind about this asphalt and concrete, as we only see those kind of surfaces in more populated areas. Rocks, ice, and grass, they're more common maybe in more rural areas, and that's kind of where we're going to take this lesson next. So again, albedo equals reflection. And again, this is kind of a general which surfaces reflect more so than others. And as we just discussed, fresh snow, really good at reflecting, therefore has a higher albedo. Between 80 to 95% of the radiation that hits this white surface actually is reflected back into the surface, into the atmosphere. The moon is really good at absorbing. Grass, again, I said that's kind of moderate, but the forests are a little bit better. They're more better at absorbing than reflecting. But again, they're not as good as absorbing as maybe a dark roof or maybe these man-made kind of surfaces such as asphalt or concrete. Brick and stone as well are decent at absorbing, but again, because of the color of these surfaces, they're very good at absorbing. And so this is kind of, again, a little bit of our energy balance here. This is from UCAR. And this kind of shows you, we're not going to spend too much time here, but it gives you the actual radiation, and what we measure of the radiation is watts. So maybe we're very familiar with watts when it comes to electricity. And this -2 means over, or so watts per meter squared. So over a square area, right? Meter squared is over a particular area. So that is kind of the units we use. So watts over meter squared. So how much energy that's watts measures amount of energy over a particular area is kind of that kind of how we measure, or the units we measure for that. And as you can see here, which we haven't talked too much about, but I think will be easy to relate to, it's pretty sunny here in northern Vermont right now. And that's also helpful because we're able to absorb, the Earth's surface is able to absorb more of the sun radiation from the sun. Whereas if we have clouds, usually cloudy days, it's cooler. Well, clouds are white, as we just discussed. White is a really good reflector of the energy. Therefore, a lot of it kind of doesn't even make to the surface on cloudy days, and the radiation kind of hits the clouds and bounces right back. We're going to continue on over here. We're going to skip this guy here. And I was definitely getting a little bit ahead of myself here, but clouds reflect sunlight and need to be included in the energy budget. If we have some low, thick clouds, maybe those kind of poofy cumulus clouds we see, especially in the summertime, fair weather cumulus clouds, or I think we got some outside today, but they look like they dissipated pretty quickly. And they're very low to the ground. They're a little bit more dense. So because they're more dense, they're really good at reflecting sunlight back, or radiation back. Where if you have those higher, thinner clouds, maybe those cirrus clouds, or those more cirrostratus clouds, those higher clouds, they're thinner. So they're actually, the sunlight, the radiation from the sun is able to kind of get through those and be able to drift down and actually make it to the surface easier. So, and you could also kind of relate this if you're outside on a sunny day, but you've got those poofy cumulus clouds coming by, you can notice it actually being a little bit cooler because of those clouds reflecting the radiation from the sun. The Earth is actually receiving the same amount of radiation from the sun when the cloud goes in front of it, but again, it's just bouncing back and it's not making it to the surface. And again, we kind of touched upon this graphic here. So what types of areas of the Earth does the Earth have? A high albedo, or a low albedo? So again, kind of touched upon this. Think urban compared to farmland and desert, which was touched upon in the video that we just watched. And as we can see here, this is another just graph about the Earth's albedo. And again, a lower albedo means a higher albedo means you're better at reflecting. So deserts are pretty good at reflecting because of the color of the sand, as well as, again, this is a large portion of the Earth that is covered in snow. Therefore, that area is very good at reflecting. As you can see here, once we get to more of these, more of the forested areas, they're definitely better at, there's a big forest through this area as well, Eurasian forests. They're really good at absorbing the sunlight because you have all that greenery on the ground. Photosynthesis is using all that sunlight to be able to grow, to help the plants grow. As you can see here in Australia, there's a big desert in the center, which is kind of good at reflecting. We're going to talk about the greenhouse effect really quickly, though, because it kind of ties into kind of how the radiation from the sun is distributed once it hits the Earth's atmosphere. And this is a great example, which I really enjoyed, is the sun's energy passes through the car's windshield. And even if it's maybe a cloudyish day, it's actually always warmer in the car because the energy is radiated from the car's interior. It doesn't pass through the windshield and the car warms up quickly. Same as a greenhouse, we talk about the greenhouse effect with the atmosphere. It's on a way bigger scale than a car maybe, or is maybe a greenhouse in your backyard. If you do grow vegetables and you go in the greenhouse, it helps trap in that radiation from the sun, and it's not able to bounce back or reflect back. It actually kind of hits the plastic or the windows, and it bounces back and forth in that greenhouse, which helps keep the temperatures warmer, which is a more forgiving climate for the plants. And again, most of the sun energy penetrates the atmosphere and strikes the earth, but some is reflected to space, which we've talked about. While some of that energy is actually radiated back into the space, much of it remains trapped in the atmosphere and helps further warm the atmosphere. So again, like that green, we call it the greenhouse effect, but the radiation is able to escape, as we talked about. Another great example when it comes to weather is if you get clouds at nighttime. So we call it actually radiative cooling. So especially if it's maybe the winter time, you have a really clear night that has snowpack on the ground or a fresh snowpack. Do you think it'll be warmer that night or colder that night? I can ask that question if anybody wants to answer. So clear skies on a cold winter night or a winter night and some fresh snow on the ground, do you think it will be colder or warmer? Thank you, Arzo there. Anybody on YouTube chiming in there, Drew?
We're kind of getting a mix of both answers. So
okay.
People have a clear one here.
So again, colder. So you would expect colder, right? So those clouds help at night. We're not receiving any radiation from the sun, but they help trap the radiation from the sun that we did receive during the day. So therefore that radiation, just like the greenhouse, isn't able to escape as fast. So if you have those clouds on you at nighttime or overhead on nighttime, you're more likely to have some warmer temperatures in the wintertime than maybe you would if it was a clear night with fresh snow on the ground. Again, that snow on the ground is really good at reflecting. I also love using the analogy is, I know we get into our bed at night and we pull the covers over. As we can see, we have plenty of covers behind me, but we pull the covers over and it's always cold when you first get in there, but after you're in bed for a little while, it gets a little warmer. And it's not like there's a heater in there. Well, maybe there is, but the way that works is, well, kind of the same as the atmosphere with clouds on it at night. We produce heat ourselves. We're warmer usually than the surrounding areas. Our temperatures are in the 90s. Usually when we sleep, it's in the 70s. So therefore our temperatures are the 60s. Our temperature is able to kind of warm up the sheets around us, but we're able to not let all that radiation that our body is giving off, because we're warmer than the surrounding area, and it traps all that radiation in, or that heat energy in bed. So therefore that keeps us warm at night. And again, you can use the same analogy with clouds at night as a blanket, just like you would when you sleep in your bed. And so what if that Earth did not have greenhouse gases? And I'm not going to get too deep into what greenhouse gases they are, but I think some of the most common one we talk about, especially when it comes to climate change, which we will not really touch on today, is carbon, which is the C, oxide is the second, and the di, so it's carbon dioxide because of the 2 there. And that's the most, I don't want to say volatile greenhouse gas we have, but that's the greenhouse gas that humans have had the most effect on. So without these, actually, we would have our average temperature of the Earth would be around 23 degrees Fahrenheit. The actual average temperature of the Earth is closer to 60 degrees Fahrenheit. So we didn't have these other types of greenhouse gases or molecules that help trap in the radiation we receive from the sun. Therefore, our Earth would be a lot colder and a lot less inhabitable. But if we, so this is a difference of about 36 degrees there, which is pretty substantial. But we also often talk about global warming and our climate change. So this is a scenario if we didn't have greenhouse gases. Well, if we put too many greenhouse gases into the atmosphere, we would have an opposite outcome, and therefore temperatures would rise. And I know a lot of people say, oh, whatever, it's a degree or two, who cares? But again, we're talking about an energy balance here, Earth's energy balance and our budget. And it's a very tight budget. So even if you kind of, put a little bit more into it, it still would have a pretty big effect on the Earth's climate. And same, for instance, if I gave someone a pay cut, if I took some money away from somebody, well, then you probably wouldn't have enough money to pay all your bills, and that would affect your budget as well. We have a question, Drew.
Yeah, one person asking, what about water? Why is H2O up there as a greenhouse gas?
So water vapor is very prevalent in the Earth, and water vapor, H2O, and it is considered another greenhouse gas. I'm not, as well as other ones, but these are the most prominent ones. So this is what we talk about in the atmosphere. Did you want to add a little bit more about the composition of the atmosphere on that, Drew?
Just in terms of the amounts of gases? So
yeah, or the greenhouse gases. If you wanted to touch a little bit more on why H2O is up there,
Well, because H2O does act as a greenhouse gas. And so that's one thing scientists are very worried about, is the fact that as the planet warms, it's possible we'll have more water vapor in the atmosphere, which means more energy and more, heat in the air. And that certainly can contribute to things like climate change. But just in terms of the composition of the atmosphere, one thing to note is that the greenhouse gases, so carbon dioxide, like Chris was talking about, they're really under 1% of the total composition of the atmosphere. The rest, 98%, 99%, is really nitrogen and oxygen. So it's important to know that the major part of our atmosphere are those relatively more inert gases.
And as you can see here, right, so nitrogen is about 78%, oxygen's 21%, and these 1%, and again, that 1%, who cares? It's just 1% is what maybe many people think, but actually it is a big deal because we are in this tight budget. We don't have this extra, I don't want to say money, but this savings account of gases or, energy that, we're a very tight budget. And I think people are familiar with a tight budget. If, when it comes to money, we can kind of apply that same concept to that, as well as to the Earth's energy balance. The greenhouse effect, again, some sunlight that hits the Earth. Oh, why do we do this again? Sorry, guys. We're going to speed through all this. That hits the Earth is reflected. Some becomes heat. CO2 and other gases in the atmosphere help trap it in and keep the Earth warm. We are very lucky that we have this atmosphere again. Sometimes they call the Earth the Goldilocks planet because we're not too hot or not too cold, just like Goldilocks porridge. Because we have this forgiving atmosphere around us, where other planets do have atmospheres, they're not the same composition as ours, and they're a little bit more volatile or a little bit not as balanced or have as much of a budget as we do. Therefore, they don't really have the best parameters to harbor life. But one point we are going to get back to, we did touch on greenhouse gases, a little bit of climate, and this kind of ties into climate change, but it also directly ties into the Earth's energy balance. And we're going to go back to talk about albedo. And we talked before that, maybe the countryside or maybe the grassy or, areas are a little bit better at absorbing, or as well as, natural surfaces kind of are good at absorbing and reflecting, where we have the cityscapes here, they're all made of concrete and asphalt, a lot of metals, and a lot of these surfaces, again, think about if it was out on a warm day and then the sun went away and you touched a piece of that metal was hot earlier in the day, or a rock or asphalt, it holds in that radiation from the sun a lot longer. Well, because of that, it will actually change the surface or the air temperature around it. If you have a warmer surface temperature, the air above it or the air around it will actually be warmer as well. So therefore, and we often use that as when we talk about road surface temperatures when it comes to weather forecasting. So, sometimes if we have freezing rain, when the temperature of the surface is actually colder than the air, rain hits the surface and freezes on the surface because of that. Drew, we have a question.
So one person's asking, is that why it feels colder when you go in a park when you're in like a big city too?
Absolutely, right? So Central Park, I don't know if there's much data around it, but I'm pretty sure if you put kind of a thermometer in the center of Central Park in New York City, it'd definitely be a little bit cooler than the actual kind of the buildings on the Upper East or the Upper West Side and around it. And again, here, we have, this is called the urban heat island effect. And that was a really great analogy there. So thank you to the YouTube listener, whoever touched upon that yes, the natural surfaces are going to be a little bit cooler than those cityscape surfaces. On a hot summer day, though, the temperature in the center of an urban area, New York City, can be 4 degrees Celsius, which is more, even higher, almost double, closer to 10 or 8 degrees in Fahrenheit, warmer than the surrounding rural areas with farms. And as you can see here, we can go to our Fahrenheit gauge. We're about 93 degrees here, where the interior of the city is about 7 degrees warmer at about 100. And again, because we have this magnitude of surfaces that are really good at absorbing the radiation from the sunlight, we get this runaway process, is what we say in atmospheric science, where the surfaces actually get hotter, therefore the air temperatures around it get hotter as well. And we do have a quick video to discuss urban heat islands right now. And this is actually a pretty big deal in science that has kind of been a part of climate change, but it's kind of been maybe more of a relevant theme, because how it also affects the weather. If you do have these temperature changes, usually, or temperature differences between the city and the rural areas or the suburbs, therefore you're most likely going to have a pressure difference. And if you have a pressure difference, therefore you'll probably have some sort of weather difference as well. There's some mesoscale or small scale weather features called a country or a country breeze, where actually there's a breeze that is able to develop because the difference of temperature between the cityscape and the countryscape. But let's see if I can get us up here really quick. And I got another quick video we can check out and pertaining to urban heat islands. Give me 1 second to change my audio here, guys. One more second, guys. Not what
typical islands. Over half of the world's population lives on urban heat islands, or places where our buildings, roads, and car parks trap more heat than the surrounding rural area. Satellites measure Earth's land surface temperature.
And we didn't even do that, guys. Sorry about that. Technical difficulties here, guys.
Lives on urban heat islands, or places where our buildings, roads, and car parks trap more heat than the surrounding rural area. Satellites measure Earth's land.
And we did see this before, right? So obviously the areas up here, which are covered in snow, really good at reflecting radiation or have a lower albedo. Therefore, they are colder.
Surface temperatures, which vary with the sky, the wind, the land surface, its albedo, and of course, the season, due to the sun's angle. Yellow shows the warmest land, while the coolest land is blue or white. Land in the tropics is always warm, while land in the northern hemisphere is warmest from June through August, and the southern hemisphere is warmest between December and February. But scientists also observe hotter temperatures in cities compared to rural areas. Increasing urbanization, or human development of natural areas, can be seen from space by our lights at night. City structures and surfaces like buildings and roads absorb more of the sun's energy during the day and emit that heat back into the air at night, making cities warmer than the surrounding countryside. This map of summertime temperature differences between urban and rural areas.
So as we can see here, this is the megalopolis on the East Coast where a large amount of people live. We're all the way from maybe southern New England all the way to kind of just south of the Mason-Dixon line. You can see it's a lot hotter in the summertime because it's so populated. There's highways, there's factories, there's buildings, there's lots of people, there's lights. So there's a whole bunch of different factors that, hey, these areas are a lot warmer. And as you can see here, we've got Japan, we've got parts of China, southern Florida is very populated. So, you know, as you see more densely populated areas, there's a correlation with warmer temperatures.
Areas shows the urban heat island effect.
You have a question?
Oh, one person just asking, what's the hottest urban area in the world?
Okay, so So that obviously, I would probably say somewhere in the Middle East, maybe, Abu Dhabi or somewhere in the United Emirates, or maybe, because there are urban areas that are in deserts as well, right? So, that's kind of tough to kind of pinpoint where the warmest urban area is in the world because it goes with the climate. But I think another good question would be to ask, if I was maybe doing some research, is where's the biggest difference of urban heat islands because of the population? So, but usually if there's a bigger urban area, there's going to be a bigger difference between, and again, same with Florida, right? Florida is going to have their urban areas are going to, on the average, be a lot warmer than maybe, New York City or Boston, because we do live in a colder climate.
Effect. Paving over natural landscapes removes the cooling effect that plants have through evaporation and water retention. Pavement makes cities hotter. Plants make cities cooler. Some notable heat islands occur in Manhattan, where nearly the entire landscape has been turned into urban area, and London, where the urban heat island effect was discovered in the 1800s. Urban heat islands have been linked to human health issues like heat stress. With nearly 2/3 of humans living in cities by 2050, we'll have to start thinking about how to sustainably develop our cities to avoid heat island effects by using things like reflective and vegetated roofs.
So again, that is definitely something that needs to be figured out. If you have more heat, then that takes more energy to cool your city. So as we can see, we have some more reflective roofs, just like the snow. This roof is white, and we all know is better at reflecting. We'll also have some vegetation on roofs because we know that it's a lot better at absorbing that energy because of photosynthesis. That's how plants grow.
And more pervious surfaces and planting urban trees. For more information, visit climatebits.org.
We had another question there, Drew?
Yeah, I think some people maybe aren't familiar with the idea of a green roof. Can you say a little bit about what that is?
Absolutely. So you know what? I'm really liking how this lesson's going because that's what we're going to talk about in just a moment. So if you guys want to hold on about a green roof, I got an example coming on the way. So Atlanta, Georgia. So this kind of shows us the urban heat islands. We actually, maybe not as extreme as New Jersey and New York, but even parts of Vermont, you could see that it's a little bit warmer. This is St. Johnsbury right here, Newport, Burlington, right? Montpelier area right there. It's kind of tight to see. But as you can see here, once we get more towards the Green Mountains in the rural area, you get a cooler temperature, even though it's only a very slight temperature when compared to maybe places like New York City or Philadelphia. But Atlanta, Georgia is nicknamed Hotlanta, and that has definitely been a big growing city the last few decades. Maybe definitely differently structured than New York City and maybe more of the older northeastern cities, as Atlanta is not as a dense city, but it's a lot more sprawling. So if you ever see the skyline there, it goes on for a very long time, but it's not as condensed as maybe downtown New York, Philly, or Boston. Also known as Hotlanta, as the city grew about 380,000 acres of trees were removed, but some forests remained around the city. The forest keeps the area and the surrounding city cool. Atlanta is an island of heat surrounded by a cool forest, an urban heat island. Oops, sorry guys. And as you can see here, it is a little bit more sprawling. So you could see maybe downtown Atlanta is not as red as maybe, southeastern Pennsylvania or central or northern New Jersey, as well as here in parts of Michigan. But this is a great example of the urban heat island effect because of that. And the next slide here is, so how can we solve this problem, right? And somebody asked what a green roof is. So a green roof neighborhood is right here. And there actually has been very progressive in parts of Northern Europe, Scandinavia, particular, as they've been very good at kind of developing these kind of surfaces to mitigate the heating effects of the sun in areas. Actually, I don't have it here, but you can Google it. It's a really cool thing to check out. They actually put a urban ski area on top of a power plant, I think in Denmark, where it's actually kind of like a grassy green substance surface, but people can actually ski on top of the surface of a power plant. But again, this special apartment building in Copenhagen, Denmark is called H2o due to its unique figure, looks like the number 8 from above. Another point though that is special about it is the building is what is growing on top of it. The H2o has a grassy, mossy vegetation on its sloped roof. And again, that is helpful at absorbing some of that sunlight, or I'm sorry, absorbing it, but also reflecting some of that energy back out to space. Unlike maybe another surface such as a blacktop. And as you can see here, you see that, you know, the blacktop is the highest here, the black roof surface is the highest. This is kind of throughout the day, so it goes down at night, but it pops back up and it takes longer to cool that surface down as well. So a quick kind of reflection to close this up. What does the Earth's albedo have on the effect of Earth's energy balance? If anybody wants to answer that question first, and I'll wait a moment for an answer. Again, what changes does changes on the Earth's albedo have on the Earth's energy balance or the Earth's energy budget?
So feel free to answer either in the chat window in our Zoom meeting or on the YouTube chat. So a few people are saying it bounces out energy, or I guess bounces out solar energy.
So yeah, so it does. So the albedo again is the kind of the reflectivity of a particular surface. If a surface has a high albedo, it's really good at reflecting back. If it has a low albedo, it's really good at absorbing. Surfaces that are really good at absorbing, rocks, asphalt, colors that are black, surfaces that are really good at reflecting are snow, as well as white surfaces, as well as natural surfaces are fairly good as well. Well, because they absorb it, but they use it for photosynthesis as well. So again, what do you think the urban heat island effect can have on Earth's energy balance? So what would happen if I paved the whole world over? We got rid of all the trees in the rainforest. We know that rainforest, taking away rainforests is not good for climate change. That is a proven fact. Or global warming, not necessarily climate change.
It looks like people are saying, well, they're answering it two ways. One is they think with the amount of cities we have now, it's not a big issue. And then other people are saying if we paved the whole world, it would be a massive impact. So I guess they're...
So again, when we think about the Earth's energy balance, it is a very tight budget. It is very thin. So I think even the urban heat islands we have now and kind of what we've paved over in the Earth now has already had an effect on the Earth. So even though it's kind of small in our minds, it actually has an impact on the Earth's energy budget because it is kind of a tight budget. And again, yes, so if we did pave over the whole Earth, hopefully that will never happen, because we would not really be that Goldilocks planet anymore, and the Earth would rapidly heat up, and we would definitely see some pretty detrimental problems to the civilization of Earth. And do you think there are any connections, I kind of hinted this, to changes, connections to climate change when it comes to the Earth's albedo? Or kind of the surface of the Earth? Again, albedo is a new word for many of us, I know, but very kind of new word, but kind of just reflecting versus absorbing. Very kind of more basic than the word really seems.
Well, one person's writing the ice is all melting. So I think they're thinking about the connection and reflection there.
Absolutely, right? So the ice caps are really good at maybe reflecting some of that back to Earth. If we have more urban heat islands, the Earth heats up. Again, that's considered another runaway process. If the Earth heats up, therefore the ice caps will continue to melt and affect the Earth's overall temperature. So again, there are connections to this. Again, if we more paved areas will affect, or these unnatural surfaces, which are kind of newer to the Earth, will affect the Earth. Therefore, there will be some connections to climate change. Yes, Drew.
I know we just have a few minutes left, but one person was asking as well, doesn't the ocean rising have an effect as well on the Earth's energy balance?
Yeah, so again, so how is where is the water from the oceans rising coming from? Well, they're coming from the ice caps, right? So even though the ocean is not the best at absorbing absorbing energy from the sun, it definitely absorbs more energy from the sun than the ice caps do, because as we know, ice caps are white. Snow is very great and very superior at reflecting. So even though there's a difference, we would still, if we had more ocean area and less ice cap area, therefore we would have this process where the temperature of the Earth would go up as well. The oceans would get warmer. And again, if you use the analogy, right, if it's 50 degrees out, but you're by an ocean that is 40 degrees, the temperature is going to be a little bit cooler by the ocean than maybe inland. Same effect if the ocean's 90 degrees and the inland it's only 70 degrees, the air temperature is going to warm up because of that as well, because that energy is going to want to transfer. Any other questions or comments or anything else we touched on today?
One person wants to know, with climate change, how does that impact the balance of things that you've been talking about? And I know you've been weaving that in, but they're wondering, I guess, more directly, does it change the balance as we get hotter?
So absolutely. Again, I keep using this word runaway process. So, kind of the computer models for the climate kind of show if the Earth continues to get warmer, it will happen faster because of that. So again, if we kind of take all these natural surfaces, they'll get warmer. And again, that process will keep kind of getting worse and worse. Drew, do you have anything else to put into that question there?
No, I think that's a really good summary. And we just have a few minutes. So I think, and obviously we can talk more about that when we do a climate change course soon, because I think, that's something we could delve into in more detail. But I think with just a few minutes left, I want to ask our final question.
I do have a question here on chat. I don't know if that's what you're going for.
Oh yeah, that's what I was going to ask.
Would be a good idea to paint the roof of my house white. So maybe, but it depends on where you live, right? So if you lived in Vermont, I probably wouldn't suggest painting your house white, because maybe it'll be a little bit cooler in the summertime, but you kind of want some of that radiation from the sun in the wintertime because it's so cold here. So if I lived in Miami, I would definitely suggest that. And if you've ever been to Miami, a lot of the surfaces are actually white. White is kind of like the official color of that city, I think, because again, it's better at reflecting the sunlight. It's a very hot climate to begin with. Where if I lived in Vermont, I don't know if I would want to paint my roof white, because I know it gets a little hot here in the summertime, but it would almost increase how much it would heat my house, because the roof of my house wouldn't warm up as well in the wintertime. Any other questions, comments?
No, I think that actually takes us to our very last minute of class today. So that was really wonderful. I don't know if you had final thoughts, Chris, before you want me to close things.
I think this is our reflection right here. So I think we summed it up. I think we hit everything we needed to that we discussed. And if nobody has any questions, thanks for everybody joining us on our virtual learning program today about Earth's energy balance.
Yeah, thank you again to everyone who joined us either in our Zoom meeting or on our YouTube live stream, or who might view this later on Kingdom Access Television. Just a reminder that the archives for all these classes are on our website at fairbanksmuseum.org. You can also find out about all the other great online things we're doing at that website front page, and as well on our Facebook page. And you can even look for more virtual learning classes like this one if you go to the Learn tab and look at the drop-down menu item that says virtual learning. We have a full schedule on there. So thank you again, everybody. And a big thank you to Chris Kurdek for leading today's class. We really enjoyed being here with you. So I hope everybody has a great afternoon.
Thanks for coming out, everybody.